Good day, everyone. Today we are going to discuss about exponential functions. So here is the outline of my presentation. Okay, first I'm going to give you a short introduction. Okay, I will not be defining first exponential function, but this introduction will lead us to understand what exponential function is, and then definition of exponential function. This will be followed by graph of exponential function and examples of exponential functions. Okay. So as an introduction, let me present to you this one. You may ask, Ma'am, what's the role of this picture that I'm presenting to you right now in relation to our topic, exponential function? Actually, there is no relationship, but this will represent to our real life application. So here is an example of a real life application that will lead us to many questions. Okay. Now, there was a study that the percent of the population who are vegans in the United States, okay, doubled from 2009 to 2011. Take note of that the population, or the percent of the population who are vegans or vegetarians in the United States, doubled from 2009 to 2011. So imagine if the population in 2009 was 100,000, for example, who are vegans, then in 2011 it became what? 200,000. From 100,000 it became 200,000. Now in 2011, okay, 2.5% of the population was vegan. Now the assumption of this, it assumed a diet that does not include any animal products. No meat, no fish, no dairy or eggs, okay, in that case. Now in 2015, vegans will make up 10% of the US population. That's one of the predictions. In 2019, vegans will make up 40% of the US population. And in 2021, vegans will make up 80% of the US population based on this study. Okay? So why I am presenting you this? Because there were a lot of questions that arise by using words that are familiar with us, but sometimes there was a question if we use the word correctly or not. So the question is like this: what exactly does it mean to grow exponentially? So when we use the word exponential, is it we are using correctly? Or what does this mean when we say exponentially or exponential? What does the word double have in common with percent increase? Or are these words used correctly? Now, we can say that we use the words correctly if we will understand or we know the real meaning of the words that I've mentioned earlier. So to understand more, let us discuss some of the definition of terms. So first, we have the term percent change. Now, percent change refers to a change based on a percent of the original amount. So, ma'am, what does this mean? So, for example, the original amount is, let's say, for example, what's the original amount? Let's say you have the original amount of something, let's say 5 pesos, for example. Okay? And then after 1 year, the original amount of that thing became 7 pesos. Okay? Now, if you are asked what is the percent change, Now, to answer that, all we need to do is to get the difference between the two amounts. So, from 5 pesos to 7 pesos, get the difference. What do we mean by difference? You are already familiar with this, right? You encounter this when you were an elementary student. Okay? Difference is the answer of subtraction. So all we need to do is to subtract. So 7 pesos minus 5 pesos. Then there is a difference of 2 pesos. Okay? Now, how to get the percent change? From this set of words, a percent of the original amount. So to get the percent change, all we need to do is to get the fraction. Okay? That is 2 over the original amount. So 2 divided by 5, 2 over 5, which is equal to what? So this one, 2 pesos divided by 5 pesos. And that is what? The answer is 2 divided by 5 is equal to 0.4. Or if we are going to convert this one in percent or percentage, this is equal to 40%. So 40% is now the percent change. Okay? Let us try to erase this. Erase. Okay, let's move on to the next term. Exponential growth. Now, what is an exponential growth? Exponential growth refers to an increase based on a constant multiplicative rate. So, multiplicative rate of change over equal increments of time. Okay? Take note of that. And one usual example of this to understand more on exponential growth is, let's say, the population of bacteria. So, for example, we have a bacterium. Let's say this one is a bacterium. And then it splits itself into 2. So, nagiging dalawa na sila. Okay? So, from 1, nagiging 2. Okay? Now, if this bacterium, this one, splits again into 2, so, this one, 2, nagiging ilan na sila? 1, 2, 3, 4. So, from 2, nagiging 4 na ang population. And then, split again into 2. So, 1, 2, 1, 2. So, you count 1, 2, 3, 4, 5, 6, 7, 8. So, from 4, nagiging 8. And then, split again. 2. So, this one. This is an informal example. Huh? So, from 8, nagiging 16, right? And so on. Okay? So, exponential growth. But later on, you will know the real meaning of this when we go to the real application of exponential growth. Okay, so let us erase. Okay, let's move on to the next term, exponential decay. Exponential decay refers to a decrease based on a constant multiplicative rate of change over equal increments of time. So, it's something like an opposite of exponential growth. Okay? So, decrease based on a constant multiplicative rate. And then, so, to understand more, let us try to compare two functions. Okay? The difference between exponential and linear function. So, let's have here a table. Suppose we have a variable x, where x here represents a real number. And we have function f of x is equal to 2 raised to x, and f of x is equal to 2 times x. Now, what is 2 raised to x? 2 raised to x, this 2 raised to x is an example of an exponential function. And 2 times x is an example of a linear function. So let's try to look at the behavior of the two functions. Now, we assign values of x. Now, in this example, we assume that the values of x start from 0 to what? So, we start from 0. We start from 0. So, we have 0. Now, what is the value of f of x is equal to 2 raised to x if x is 0? So, how can we solve that? We are going to evaluate the function at x is equal to 0. Now, in your high school, evaluation of function is just simply substitution or substituting the value of x to the variable x in the function, right? So, if you are going to substitute 0 to this function, 2 raised to 0, so any number raised to 0 is equal to 1. And here, if you are going to substitute 0 to this linear function, it becomes 2 times 0, which is equal to 0. And then, if x is 1, then 2 raised to 1 is 2, right? Then 2 times 1 is 2. Okay? So what have you noticed? If x is equal to 1, the function value, the exponential function, and the linear function have the same output value, which is 2 and 2. Okay? Now, how about if x is 2? If x is 2, so all we need to do is to substitute 2 to this function. So we have 2 raised to 2, which is equal to 4. And 2 times 2 is equal to 4. So we have noticed that if x is equal to 2, the function value, the exponential function at x is equal to 2 is equal to 4, which is equal to the function value of this linear function, right? Okay, equal. So if you are asked what value in the domain wherein the exponential function and the linear function produce the same output, then your answer is if x is 1 and if x is 2. Okay, now how about if x is 3? So simply substitute. 2 raised to 3 is 8. 2 times 3 is 6. If x is 4, 2 raised to 4 is 16. 2 times 4 is 8. If x is 5, 2 raised to 5 is 32. 2 times 5 is 10. If x is 6, then 2 raised to 6 is equal to 64. And 2 times 6 is equal to 12. Now, please make an observation based on the table that we have. What's your observation? Okay? What's your observation? Maybe you will say that, Ma'am, if x is greater than 3, let's say 3 to 6, right? Then the function values, okay, or 2 raised to x is what? If x is, let's say, 3 to 6, okay, the function values or f of x is equal to 2 raised to x becomes bigger than the function values of f of x is equal to 2 times x. Okay? Take note of that. And also, as your exercise, try to include values of x that has a fraction. Let's say 1 and 1/2. So what is the value of this function if your x is 1 and 1/2? Okay, So that's your exercise. Any observation? Okay. What's your other observation? Maybe you will say that you notice as x increases, it's like we double the function value, the original function value. For example, the original function value of the exponential function is 1. Then, if x is 1, it becomes 2. Okay? 2 times 1. 1 times 2 is 2. If we increase the value of x, let's say 2, then it becomes 4. Like we are just simply multiplying 2 to the original function value. Let's say 2 times 2 is equal to 4. If x is 3, then 2 times 4 is equal to 8. So we're just simply like multiplying the original function value by 2. How about this one? What have you noticed? If x is 0, then the function value is 0. If x is 1, meaning you increase 1 unit, then the function value becomes 2. And then 4, and then 6, 8, 10, and 12. So any observation? We're just like simply adding 2 to the function, original function values of the linear function. Okay? Okay, so let's try to compare the graph of the two functions, the exponential function and the linear function. So as you can see, if x is 0, this one, if x is 0, the function, the linear function 2 times x is 0, right? So 0 siya. So dito 0, 0. Now if x is 1, the function value of the linear function is 2. So 1, 2. Okay, this is 1, 2. Which is the same as the function value of this exponential function, right? If x is 1, so 2. That's why if you are going to look at the graph, it intersects at the point 1, 2. Because they are having the same function value if x is 1. How about if x is 2? This one, if x is 2. If x is 2, the function value of the exponential function is 4. So let's try to look at this graph. 2, then 4. So this is 2, 4. Okay? And also, the linear function is 4. That's why, looking at the graph, we can say that the two functions intersect at 1, 2, point 1, 2, and 2, and 4. Okay. Now, how about if x is 3? If x is 3, the function value of the exponential function is 8. So if x is 3, this one. So this is 3, 8. Okay, 3, 8. And the linear function, 3, 6. So what have you noticed? If x is 4, the exponential function value is 16. Okay, while the linear function value is 8. So what have you noticed? What have you noticed? We notice that the exponential function grows very fast or faster compared to the linear function. Okay? Now, here is another term. Exponential growth refers to the original value from the range increases by the same percentage. Okay, the same percentage. For example, we just simply like doubling the function value here, right? While the linear growth refers to the original value from the range increases by the same amount. So, kanina sinabi natin na para lang tayong nag-add ng 2 units. Okay? Range increases because we are looking at the values in the range, the output values, because recall that the range is the set of output. Okay? Okay, let's move on to the next slide. So let us examine another same example of an exponential function to really understand what is an exponential function and what are the characteristics of an exponential function. So let's define the behavior of the graph of the exponential function f of x is equal to 2 raised to x. Okay, again, if we have values of x, -3, -2, -1, 0, 1, 2, 3, then we just simply substitute the values of x to the function value, or to the function 2 raised to x in order to get the function value. So 2 raised to -3 is equal to 1 over 8. 2 raised to -2 is equal to 1 over 4. 2 raised to -1 is equal to 1/2. 2 raised to 0 is equal to 1. 2 raised to 1 equals to 2. 2 raised to 2 is equal to 4. 2 raised to 3 is equal to 8. Now again, let us examine the behavior of the graph. So by simply plotting the points, we get this graph. So for example, we have -3 and 1/8, this is the point. -2 and 1/4, this is the point. -1 and 1/2, this is the point. And 0, 1, so this is the point. This one, 1, 2. This one is 2, 4. And this is 3, 8. So assuming that we do not know the behavior of the graph, all we need to do is to plot the points and connect the dots. Okay, connect the points. Then we were able to sketch the graph of the exponential function 2 raised to x. Okay? Now another observation. Any other observation? Important characteristics. Take note that the domain of the function, exponential function f of x is equal to 2 raised to x is -infinity to infinity, or simply these are. What does this mean? This is set of real numbers. Set of real numbers. Okay? This is a notation. This is a notation for the set of real numbers. So in interval notation, we write the set of real numbers like this. Okay? So if we enumerate the values in the set of real numbers, we can also have this one using the opening and closing braces, or open braces, and this one closing braces, by just enumerating the values. Let's say -3, -2, -1, 0, 1, 2, and so on. Okay? Now, you may ask, Ma'am, is a fraction, let's say 1/2, included in this set? Yes, a fraction is an example of what? It is a rational function, a rational number, which is included in the set of real numbers. How about irrational? Let's say square root of 2. Is square root of 2 a real number? Yes, and that is an example of an irrational number. Okay? So take note of that. So the domain, meaning the domain is the set of input that can make the function defined. So meaning to say, for every number in the set of real numbers, the exponential function becomes defined, or is always defined, whatever number which is in the set of real numbers. Okay? Whatever the value in the set of real numbers, if you input that one to the function 2 raised to x, then the function 2 raised to x is always defined. Okay? Meaning it always exists. How about the range? The range of this function. Take note that the range is the set of outputs, right? The set of y values. Now, by just looking at the graph lies above the x-axis, or this is y is equal to 0. Okay, y is equal to 0. It lies above the y is equal to 0 or the x-axis. Meaning to say, the y values, okay, the range or the set of outputs is 0 to positive infinity. That is the range. Okay, or we can also have, in set builder notation, we can have this one. Y such that y is greater than 0. Take note that y is any real number. So y represents any real number. Okay, y is greater than 0. Okay, take note. Let's erase this one. Okay. Now, another characteristic of this function, as x approaches to positive infinity, so negative infinity, negative 5, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, and so on, up to positive infinity. Okay, as x approaches to positive infinity, you look at the graph, the behavior of the graph, okay, the function increases without bound. So as x approaches to positive infinity, f of x approaches to positive infinity also. Okay? Now, as x approaches negative infinity, so we start from here, from positive infinity. As x approaches to negative infinity, from the right going to the left, okay, as x approaches negative infinity, the graph approaches to what? The graph approaches to 0, meaning the graph decreases, okay? But it will never be equal to 0. Why? Because, ano kaya ang reason? The reason is, this y is equal to 0. This is the asymptote. Asymptote. Okay? So another observation, f of x is always increasing. Okay? This one is increasing as x approaches to infinity, as what we have discussed earlier. Now, the graph of f of x will never touch the x-axis. Okay, this one, do not assume that this graph touches the x-axis. No. The graph of f of x will never touch the x-axis because base 2, okay, this one, base 2 raised to any exponent never has the result of 0. Why? Because even if our x is 0, this function, the function value is always 1. Because 2 raised to 0 is equal to 1. Okay? So, this function will never be equal to 0, or will never produce a result which is 0. Okay? And as I've said earlier, the reason why this function never touches to this x-axis or y is equal to 0, because y is equal to 0 is the asymptote or the horizontal asymptote. Now, recall in your high school, an asymptote is a line that continually approaches a given curve but does not meet it at any finite distance, right? Okay. And then, in this example, 2 raised to x, the y-intercept is 1. This is the y-intercept, right? The y-intercept is the value of y when x is equal to 0. Okay, so 0 and 1. That's the y-intercept. Okay, so we have here the definition of exponential function, or the general form of exponential function. You take note of this because this is very helpful in understanding different types or different examples of exponential functions. So here, for any real number x, so assume for any real number x, we have this one. For any real number x, an exponential function is of the form f of x is equal to a times b raised to x. So in other words, kanina yung example natin na f of x is equal to 2 raised to x. This is an example of an exponential function. So in this case, what is our a? Because the general form of an exponential function is this one. So in this example, what is our a? Our a is 1. What is our b? Is 2. Okay? Okay, very good. So, but you have also to take note the different conditions. These are very, very helpful and important. So you take note of this. So where a, this a is a non-zero real number. So when you say non-zero real number, so it could be negative or it could be positive. Okay? But not equal to 0 because non-zero real number. Now, what do we call this one? Non-zero real number, this a here. This is what we call initial value. And another condition, b, our b is any positive real number such that b not equal to 1. So when we say positive real number, that is b greater than what? Greater than positive, when we say positive, greater than 0. But with the condition that b must not be equal to 1. So, for example, is b can be 1/2? Yes, b can be 1/2 because 1/2 is greater than 0 and not equal to 1. Okay, so is b can be, let's say, 1.5? Yes. P, okay, B can be 1.5 because 1.5 is not equal to 1. Okay. Now, the domain of F, take note that the domain of F is all real numbers. Again, kanina, when we discussed the example 2 raised to x, the domain, let's say D, negative infinity to positive infinity, or R. Okay? Now, the range of F is all positive real numbers if A is greater than 0. So, there is a condition that the function value, okay, the range of F is all positive real numbers. Okay? Meaning to say the graph of the exponential function looks like this with the condition if A is positive. Okay? Why? Because if A is positive and B is always positive but not equal to 1, then this will be positive and the function value is increasing, right? Now, there's another condition that the range of F is all negative real numbers if A is less than 0. So, if A is less than 0, because the condition of A is non-zero real number, it can be negative, meaning to say the function value becomes negative. Okay? So, we can have this graph, for example. If this one is increasing without bound, this one is decreasing without bound. Okay? Now, the y-intercept is 0 and a. What is a? A is the initial value. And the horizontal asymptote is y is equal to 0. Okay, take note of that. Now, in our example 2 raised to x, the intercept is, recall, the intercept is 0, 1, right? Because by the general formula, the intercept of the exponential function is 0a. And since our a here is 1, that's why the intercept is 0, 1. And the horizontal asymptote is y is equal to 0. Take note of that. So if the question is, can we assume the function value to be negative? And I think that's one of the questions in your exercises or problem set, but you need to answer that. I will not be the one to answer that. But based on this condition, you have to understand if we can assume the function value, the exponential function value to be negative. Okay? And the hint is by this condition. Take note. Then the y-intercept is this one. Okay, so let's move on to the next slide. Okay, so we have here a family of exponential functions. Okay, take note that this graph is the graph of 10 raised to x. So meaning we have an exponential function which is equal to 10 raised to x. So our base is 10, and this one, our base is 4, and base is 2. What have you noticed? Notice that all of these graphs pass through the same point, 0, 1. Okay. 0, 1. Why? What's the answer? Because, as I've said before in the previous slide, the intercept, this one, the y-intercept, the y-intercept is 0a. And in this example, our a here is 1, is always 1. So 1 times 10 raised to x, 1 times times 4 raised to x, and so on. Because this is 0 and 1, because b raised to 0 is equal to 1 for b not equal to 0. Okay? Now, what else? Any other observations? Now, maybe you have observed that as the base decreases, let's say 10, 4, 2, okay? Or let's say as the base increases, the graph of the exponential value, the graph of the exponential function becomes closer to the y-axis. Tingnan natin, since ang 10 is malaki siya compare sa 4, right? Pero mas malapit siya doon sa dito sa y-axis. Ang 4, okay, medyo malayo na siya compare sa 10. And then, if you're going to look at 2 raised to x, mas malayo siya dito kaysa 4 raised to x. Okay. Now, what happened if our base is less than 1, but greater than 0? So, that means we are referring b here as fraction. So, what happened? So, take note, if we have a b which is a fraction, meaning less than 1 but greater than 0, the graph decreases. Meaning, as x approaches to positive infinity, the graph approaches to 0. And let's see, for example, this 1/2 raised to x. Okay? It decreases. But take note that if the denominator, okay, as the denominator increases, let's say this one, 4 is bigger than 2, right? Notice that the graph is closer to the y-axis. Okay? So this is a family of exponential functions, and try to examine this graph. Okay? Now, if b is greater than 1, ito yon. If b greater than 1, then b raised to x approaches 0. Okay, this one. If b is greater than 1, this example is 10 raised to x, 4 raised to x, 2 raised to x, right? Now, it approaches to 0 as x decreases through negative values. Meaning, if we're going to look at the x values and we start from the right, let's say, as x approaches to negative infinity, this function value or exponential function approaches to 0. Okay? This one. But if we are going to start from here, from the left to the right, as x approaches infinity, then the function value or the function increases without bound. Okay? Take note if b is greater than 1. Okay. So another important remarks. Now, if x is equal to 0, take note that b raised to 0 is equal to 1. And if x is equal to negative n, then b raised to negative 1, and negative n is equal to 1 over b raised to n. For example, let's have an example. So if you have b raised to 2, so you follow this formula, this is equal to 1 over b raised to 2. Or specific example, if 4 raised to negative 2, then that is equal to 1 over 4 raised to 2, which is equal to 1 over 16. Okay? So take note of the important remarks for an exponential function. Okay. Now, if x is rational, is a rational number, meaning is of this form, x is equal to p over q, where p and q are integers, and q is greater than 0, then this one holds. Meaning, you have a base raised to x, and then if the exponent is a rational number, let's say 1/2, 3 over 4, then this b raised to x becomes b raised to p over q, right? Which is equal to qth root of b raised to p, or which is equal to this one. Okay, so for example, you have, let's say, 2 raised to 1/2, for example. Okay, 1/2. Actually, if the exponent is 1/2, that is square root. Because by using this property, 2 raised to 1/2, we have square root. Supposed to be, we need to write 2 here. But since we know that that is square root, so it's okay that we don't write 2 in here. So we have 2. Square root of 2. Okay? Now, for example, if we have 2 raised to 2 over 5. So this is equal to, using this property, we have what? Fifth root of 2 raised to 2, which is equal to the fifth root of 4. Okay? So take note. Another important property. Okay, so we have here what we call natural exponential function. Now again, this is the general formula or general form of an exponential function, but in this case, our a is 1. Okay? Now, the value of e, correct to 5 decimal places, is approximately equal to 2.71828. Okay? So in this case, the base is now e, which is approximately equal to this number. Now, this is what we call the Euler's number. Okay? Euler's number. You pronounce this as Euler's. Before, I pronounced this as Euler, but we pronounce this as Euler's number. Okay? So take note. Now, the base is e. So, we call the function f of x. If the base is e, so it becomes f of x is equal to e raised to x. And we call this function as the natural exponential function. Okay? So this is the graph of the natural exponential function. And m is equal to 1. What is m here? It's the slope. Okay? So here, it comes as no surprise that the number e, take note of this graph. This is the graph of y is equal to 3 raised to x. This one is the graph of y is equal to e raised to x, and this one is y is equal to 2 raised to x, right? Now, it comes as no surprise that the number e lies between 2 and 3. Because I've discussed this earlier, that as the base increases or as the base becomes bigger, the graph becomes closer to the y-axis. And since the function is 3 raised to x is bigger than 2 raised to x, this 3, 3, okay? So the 3 raised to x, the graph of 3 raised to x is closer to the y-axis as compared to 2 raised to x. But also, the function y is equal to e raised to x, we expect that it lies in between these two functions. Why? Because the function value or the value of the Euler's number is 2.7, which is greater than 2, right? So, if you compare the Euler's number to 2, it must be closer to the y-axis. But again, if you compare it with 3 raised to x, 3 raised to x is closer to the y-axis. Okay? So take note of that. Okay, so that's it. Thank you very much. And if you have questions regarding our discussion today, you can just message me, you can email me, or you can message me via the messenger or the email or the VLE messaging feature. Okay? So do not hesitate to ask questions if you have questions. And then hope that you learned something from this video, and I hope that you will also share the learning that you got from this video. Okay, so don't forget to share the learning that you got from this video. Thank you very much, and thank you also for your time in watching this video. Bye!